So our next speaker is Jonathan Cloutier from Codes down at the University of Tasmania, and he's going to talk to us about the SWAN deposit.
All right, hopefully you can see the screen.
Yes, perfect.
Should be all right. All right, so hello everyone. I'm Jonathan. Today I'm going to be talking about silicate mineral chemistry as an exploration tool at the SWAN IOCG deposit. And this is a picture here at the bottom of where we were doing field work. China was in an outdoor courtyard, just remembering the time where we were allowed to be outside and be able to look at the rock and sampling the core. I also want to acknowledge my co-authors, Steadman, Shaun, and David Cooke. Let's see if I can move this. Also want to acknowledge, before I get into the details, the Geological Survey of Queensland through the Strategic Resource Exploration Program that allowed us to do that project. China Resources that allowed us access to the property and be able to sample the deposit. CSIRO for providing access to archive samples, and the analytical laboratory staff at Codes have been really instrumental in that project as well. So before I go too much, I want to talk a bit about the mineral geochemistry vectoring. This is built on the premise that gangue minerals and hydrothermal alteration assemblages are sensitive to changes in fluid chemistry and temperature. That could be either sulfides, like is the case on the image on the right. It could be silicates, it could be oxides, it could be carbonates, or it could be phosphates. And what we see here on the right is two laser ablation images of a pyrite grain and a magnetite grain that's interlayered. So what you see here is the magnetite here sits in that kind of green area, and it's been replacing some of that pyrite crystal here. So these different bands corresponds to cobalt on the left and nickel on the right. So depending on the temperature of that color, if it's really red, it means it's higher concentration. You can start to look at the chemistry of the mineral, or also the evolution of the chemistry of that mineral based on that different phases or different bands that occurs within these minerals. Together, these characteristics enable us to provide fingerprints and footprints of deposits, which means fingerprints means that you can have a geochemical understanding of the minerals and or that forms the deposit, and the footprints means that it's identifying the geochemical dispersion halos around these deposits. And together, these can aid mineral exploration by measuring the chemistry of these individual mineral species or combine several mineral species. And today we'll focus mostly on silicate, and I'll show you the results of what we've done for this silicate work. But before I go in details, I want to talk a bit about the mineral chemistry that's been undertaken at Codes. It's the utility of mineral chemistry in porphyry epithermal exploration was demonstrated through a series of AMAR projects over the last 15 years at Codes. And there was a particular focus on the green rock environment where there's porphyritic alterations. The premise of that study here is that IOCG's deposits have large footprints. So how can we use mineral chemistry to vector to these deposits as well? Can we use the method? What's the dispersion halo? What type of elements are moving? These are the type of questions I will be trying to answer through that project. Moving straight into the SWAN geology, I made here a cross section. There's different things to observe in that cross section here. I'll walk you through the main things here. The different colors in the background relates to the different geology. There's a legend on the left side here for these different geology. The blue refers to marble. The yellow is a quartz mica schist that tends to be sitting on top of the sequence here at SWAN, or more on the east side. There's a mafic intrusion in green, and it's the whole rock types here are cross-cut by late dikes that are post-mineralization. One thing that you can see here is this kind of red outline here, which is the outline of the SWAN 0.25 copper equivalent grade shell. So this is pretty much the highlight of the deposits. And most of the SWAN deposits hosted in that blue unit, which is in the marble in this area. The other thing that you can see on the screen here is that black outline that's sitting outboard of that red outline here. And this is the alteration outline. So this is anything in the core logging from China that was either described as breccia or calcilicate or skarn, and just combine them together and to form an alteration halo. As what you can see here, that the scale of that cross section sits on the bottom left side here. So we have a kilometer. So the extent of alteration outside this mineralized halo is very limited. You can maybe have 100 to 150, maybe all 200 meters at max. But the alteration halo is very small compared to the deposit. So can we actually find some bigger trends associated with the mineral chemistry? So in terms of mineral chemistry, we've looked at, for this project, amphiboles, apatite, chlorite, epidote, and pyroxene. And I'll present the amphibole here, and I'll show a summary of everything else. And before I go further as well, we sampled a whole, these different holes that we sampled here, these little straight line. We did the whole numbers that we sampled. 3 of them were from the main system, where they just got through the SWAN deposit proper. So there's the different 3 holes, but we also had a hole that was sitting 1.8 kilometers away from the deposit to the northwest that we wanted to use as background, or actually see if we can see if there's any signature of other SWAN type or SWAN similar system sitting over there. So that's the main things that we want to do with this. So going up to the results, this is amphibole chemistry. I'm just going to show you this one, and after that, I'll show you a summary slide. But basically what we've done, we've taken a bunch of samples. What I've done here, the different colors refers to the different rock types. The legend is at the bottom right diagram here. We have the blue is the marble, the yellow is the quartz mica schist, is amphibolite. It's just different quartz mica schist as well. Mafic intrusions and the diorite. And the distal hole is sitting on these right side of this panel, so at around 1500 distance here. So the x-axis is the distance. So 0 here is where this 0.25 copper equivalent surface or ore shell is. So anything in the red zone is within that deposit. So you can actually calculate the distance inward from that deposit to do these type of things. On the y-axis, there are these different elements. So basically from these elements, what you can see is if we look at the case of the vanadium, it starts really high, around 4 to 500, 3 to 400 ppm in the amphibole. And as you move away from the deposits, there's a general trend that's moving downwards in that direction up to around 600 meters, which is the extent of our sampling. And if you go to this distal hole, it tends to be at around 100 ppm there. So there might be, well, there definitely is a decline or decrease in concentration of vanadium with distance to the SWAN ore body. And this is true as well, regardless of the ore type. There's marble in blue, there's mafic intrusions in green, and then these like orange one is this quartz mica schist. They all show a progressive decrease as you go down in vanadium. The same thing is true with the chromium. There might be a bit of a plateau up to 100 to 200 meters, but there's still a decrease associated with that. And it doesn't matter, again, if it's the marble in blue or the mafic intrusion in green. They're both showing somewhat of a decrease as you move away from the deposit. And the distal hole tends to be very similar to what we have in terms of value at around 600 meters. We see something similar with strontium in amphibole. Again, there's a progressive decrease as you move away from the deposit. It might be a bit more limited than with the vanadium and the chrome, but there's still some kind of decrease. And for the manganese, we see the inverse relationship where it starts low around the deposit and it's moving upward up to 10,000 ppm, 1% manganese when you get really thoroughly into the marble. So that might be an effect potentially with the marble, but overall, regardless of the rock type, in this trend here, there's an increase in manganese. So really what we see is that from distance from the ore zones, there's a decrease in vanadium, chromium, and strontium in amphibole, and an increase in manganese. And all these variations are independent of the protolith. This is something that we wanted to check to make sure that there's no effect of protolith, and we see these trends happening that are not associated with the deposit or the rock type. All right, so in terms of mineral chemistry summary, this is my last slide on this mineral chemistry. So basically, it's the same diagram as before with the red outline here of the 0.25 copper equivalent of SWAN, this alteration halo here. And what I've done here is doing all these different minerals. So the amphibole, the manganese concentration increases with distance from the deposit. That's what this arrow means when it's going outside the deposit. And this concentration increasing vanadium, chromium, and strontium increase towards the deposit. The other minerals that we've looked at is apatite. There's a vanadium that is increasing towards the deposit. Sodium and arsenic shows a depletion halo surrounding the deposits, and it's just going back up again with distance up to 600 meters. Phosphorus show an increase in an increased halo or an enrichment halo around the deposits. If you go to the chloride, there's increasing amount of chloride or towards the deposit itself. So there's more vanadium, tin, and yttrium towards the SWAN ore body. And there's a decreasing of titanium strontium ratios that's been used in porphyry deposits to look at distance to heat centers, zinc and nickel as well. There's a decreasing relationship, between silica, manganese, lead, and lanthanum. So just a halo here that's decreasing. In terms of epidote, we've looked at there's definitely an increase in nickel when you're going closer to the deposit. There's a depletion halo for the tin and an entrenchment halo for the arsenic and the lead. And in terms of pyroxene, there's an increase in the concentration towards the deposit, potentially a decrease of manganese away from the deposit. Sorry, an increase in manganese away from the deposit, a depletion halo of tin and ytterbium, and an entrenchment halo and vanadium on the shoulder of the deposit. So this is the main characteristic that we see from this. So in summary, what we can see here is the mineral chemistry extends the geochemical footprint of SWAN considerably, much bigger than the alteration halo. And if I go just back one, just to show you that point again, this is the scale on the bottom left corner, it's 500 meters. So we can see an alteration halo up to 600 meters or so from that red line here. So it's not just from the middle of it, it's from that red line. So you would extend pretty much all the way to here, which would be much bigger than the visible alteration halo at SWAN. So this is something that we can do with the mineral chemistry. That's what I was saying. The mineral chemistry variation over is 600 meters have been detected around SWAN, and the visible alteration extent tends to be less than 200 meters. There's been multiple alteration minerals that are showing geochemical trends that are potentially useful for exploration. And as a question I have you at the end is that sample on the right. If you collect that sample, this is from the SWAN deposit, and it's a magnetite vein with pyroxene and amphibole and a bit of epidote and a bit of albite. It's this hematite stained albite on the right. These bit here, would you be able to say how far you're out from the deposit? And from that mineral chemistry, we'll be able to at least predict if you're getting closer or further away from that deposit. So thank you.
Thanks, Jonathan. We have a couple of questions for you. Mike Whitbread is asking, what composition of amphibole did you target?
Basically, we were not trying to discriminate too much. Anything that looked like, well, that had the chemistry of an amphibole. There's definitely different types of amphibole sitting in there, but we did not discriminate about which type we were looking at. And it basically, the chemistry of the amphibole is just in equilibrium with the fluid, so that you're tracking a change in amphibole chemistry, and there will be a change in mineralogy as well. But it didn't really matter for that study. It was just mostly the chemistry in the amphibole that were responsible for the change.
Okay, and George Gibson would like to know, to what extent do you think that the geochemistry of alteration reflects the presence of older mafic volcanics at depth? Say something akin to the ECVs, the Eastern Creek volcanics, or the Moraba volcanics, or their equivalents?
Yeah, that's a very good question. In terms of the mineral chemistry of the silicates, we can see that they're independent of the rock type that's present there at the site. So the alteration halo is varying really well with distance from that chemistry. But I would not dismiss the potential presence of some kind of mafic volcanics or intrusive that would provide some of these elements. I mean, there's a lot of iron in there, there's a lot of copper, there's a lot of gold and sitting in these systems. So they have to come from somewhere. But I'm not quite sure in this area if there's any geological units. I mean, there is these mafic intrusives that are sitting near the deposits, and I didn't spend too much time talking about it, but there is some, the timing of it needs to be a bit redefined, but I would not be surprised if when we date it, it's going to be somewhat similar time, similar age and mineralization. It sits right in between SWAN and Mount Elliott, and there's a little bit of mineralization in the mafic intrusion, not much. There's still a little bit, and it's not fully mineralized, so I wouldn't be surprised if it played a little bit of a role, but we need to do more work to be to be sure.
We'll move on very quickly in a moment, but Richard Lilly has made a comment to that the amphiboles paragenetically predate sulfide deposition at all Cloncurry deposits. So given that these minerals are not directly associated with sulfide mineralization, would you ascribe their various geochemical variations away from the core of the SWAN system as simply a factor of chemical partitioning in the fluids as they cool down, as they travel away from the structures controlling fluid ingress? That's a really long sentence, Richard.
Yeah, and it's a very good question as well. We've been thinking about this a little bit, and I totally agree with you. When you do the paragenetic sequence at SWAN, they basically the sequence you see is there's early albite, and then there's magnetite, amphibole, with potentially a bit earlier pyroxene, so maybe pyroxene and then magnetite, amphibole, and then it will move on to pyrite and chalcopyrite, and so there is a transition. It's either are you thinking about, is it one system that's evolving through time to do that series of mineral that goes from more reduced environment to more potentially more oxidized when you start having there's some anhydrite veins sitting in these type of things. So there's definitely some more oxidized fluids that came in through the end or towards the mineralization stage. Are they part of a fluid partitioning, controlling? I'm not quite sure. We still have to think about this. I'll be interested to hear your ideas about that. But there just definitely seems to be an evolution between a more reduced earlier phases and the more oxidized phases, that the earlier assemblages are used as a reductant for this newer pulse of oxidized fluid overprinting the system. So there's definitely two things that needs to be overprinted on top of each other. And the chemistry of the amphibole per se seems to be reflecting this interplay between these more reduced and more oxidized fluids. I don't know if that answers your questions.
I think that if there's further discussion, we might pick it up at the end.